All right, so now we are on to 1.4 functions describing change. So in 1.3, we kind of abstractly talked like this is how you make a model. B, we kind of gave like a loose definition for. A was our initial value. That one's pretty straightforward. And then we talked about how we could use models to predict. So now, and we kind of talked about how do I know? Like we talked about temperature versus elevation, and it kind of got a little like, oh, you just know. So now we're kind of putting more context into that. All right. So in previous sections, we created models, which we study these models using the concept of what is called a function. And I think I mentioned that word already. So first, we're going to talk about what is called a relation. Relation. So relation is a rule that sends a value to another value. Um, elevation sends me to this temperature. This depth sends me to this pressure, so on and so forth. But a function is a relation. So within relation, I have an option to also be a function in which each input gives exactly one output, which is really nice. So a relation can give us multiple outputs. Think about pay rate for years you've been there. So many people can be working there for a year and have very different pay rates. So when your experience working at a company could give you lots of different pay outcomes. So that wouldn't be a function because that doesn't give us exactly one output. But if we talk about pressure, I'm not going to have, who's calling me? I'm not going to have two different pressures at the same depth in the ocean. That would be weird. Oh, okay. So we can identify a function if each input gives exactly one output. So if we want to think of x as our input and y as our output, every x sends me to only one y. Okay, so we're going to identify which is a function. So if we're looking here, my inputs are 1, 2, 3, and 4. So 1 sends me to 10, 2 sends me to 20, 3 sends me to 30, and 4 sends me to 40. So does each input send us, so right 10, and then when we say send us with that arrow, to one output? Yes, everyone goes just to one other place. So this is a function. And now sometimes you'll also see me write function fxn, not that, I think that's a TV channel too. But that's just another way of writing function. Okay. What about in B? So 1 goes to 10, 2 goes to 20, 2 goes to 30, 3 goes to 40, and 4 goes to 50. I would say that this is not a function. You are not a function. And that is because 2 goes to 20 and 30. So I can only have one output and this one has 2. Therefore, it is not a function. Okay, pretty straightforward, I think. I hope you can read that. I don't know where my little head is floating. Coolio. So we don't have to look at these blobs. We can also just look at a table kind of like this. So we can see that these tables, and then I would say like the input would be the year, and that they would map to something like that. Okay. So remember, the input can only have one output, but that output, there's no restriction on what the output is doing. Okay. So so we have year and the number of women in the Senate. How many women are in the Senate now? Curious. 24. Cool. So in 1999, there were still 9. In 2001, 3, 5, and 7. Oh, sorry, just 5. They each had 14 and then 16. So does every input have one output? Yes. This is a function. Even though these two things have the same output, that's fine. But that input, the year 1997, isn't going to 9 and 14. It's just going to 9. Each year is just giving me one output. It's okay that it's going to the same thing. So basically, my inputs kind of have to be faithful. They can only go to one output. My output, my Y, in a sense, is non-monogamous. It can have multiple inputs associated with it, kind of thinking on that line, right? So the output in this scenario, if we're just talking about a function here, just because there's the same output for multiple inputs, that's completely fine. We'll talk about a different function or a specific type of function where every input has one output and that output only has that input. Right, so this is a function. Moving down. So age of women and number of children. I did not come up with all of these women-focused charts. These are what are in the textbook. Okay, so we have a 30-year-old. Oh my God, not 9. Oh my God, I forgot to change this axis. That was the same for the Senate one. I like copied and pasted. That's really embarrassing. I was like, this woman has 9 children. It's coming for you, Michelle Duggar. Okay, so this is not what this should be. I have them in front of me though. So it should be 3, 0, 1, 1, 2, and 0. Okay, jeez, about to give me a heart attack. Okay, so a 31-year-old has 3 children. A 32-year-old has no children. 24-year-old has 1. A 35-year-old has 1. A 31-year-old has 2. And a 22-year-old has 0. Okay, so a good indication, if we're trying to find a function when we're looking at a chart like this, is look for similar inputs. So I have a 31-year-old here and I have a 31-year-old here. So 31 is going to 3 and 31 is going to 2. So this is not a function. Thank God. 31 has 2 different outputs. And it's important to note that they're different. If they were the same, it would be a function, but they're different. Because it's 2 same outputs, it's just saying it's one output. Okay. I think that's my only repeater. Yeah. Okay, cool. So now this kind of the next section kind of harps back onto what we were talking about. How do I know which is on whose side on that equation? So we say, so which 2 variable data represents functions? So we say y is a function of x if each x is that's usually our input, corresponds to exactly 1 y, our output. So in this case, x is what we would call the independent variable, and y is the dependent variable. So when y is a function of x, that would look like a y equals, and then something with x involved, and then something else. Okay? So y depends on x. A common independent variable is time. Time waits for no man or woman or in between. So an independent variable like time, that's not ever going to depend on something unless I'm recording it, right? Like if I'm recording how long it takes to do something, that time is a little different in the sense of time just continuously passing. And then y being my dependent variable, it makes sense if you look at this kind of equation. I can plug in any x, work out all these numbers, and then I can get that y back out. That y depends on what value of x I put in. You can also see that if I put my input, that's going to be my independent variable. So you can kind of see that as a little bit of a pattern as well. All right. So which equations represent functions? So you've only kind of looked at charts right here. And I can't make linear models from things that aren't functions. So an equation gives a set of ordered pairs, and we usually call those x, y's, right? So for example, y equals x squared would give us the set of these ordered pairs. When x is 0, y equals 0. When x is 1, y equals 1. That's supposed to be a negative. When x equals -1, y equals 1. When x is 2, it equals 4. When it's -2, it's also 4, and so on. So we see these two inputs have the same output. But again, that's allowed. That's fine. So an equation is a function if the corresponding ordered pairs is a function. And we're not going to look at every ordered pair. There's infinite amount. We talked about a few sections ago, continuity. Like I could plug in 0.4375 continuous, whatever. And that would give me an output, but I'm not going to make that one my ordered pairs. That's weird. I want to kind of only look at ordered pairs of whole numbers. It just helps me out. And by whole numbers, I mean when x is a whole number. Great. And then if you wanted to even draw, I've seen people draw them as charts because I think writing ordered pairs is kind of confusing. So if you draw a chart, it'd be like 0, 0, 1, 1, -1, 1, 2, 4, and such and such. So that's another way that you can take ordered pairs and make them a chart that makes them easier to see if they're a function. Okay. So, okay, so now let's look at this equation and we're going to be asked to find if z is a function of w. So if I want z is a function of w, we say y is a function of x, means we're going to have a y equals scenario. So to find if z is a function of w, I want to find z equals. Right now I have 5z plus 2w squared equal to 8. Okay, so I have 5z. I want to solve for z. So I'm going to move 2w squared to the other side to get 8 minus 2w squared divided by 5 divided by 5. And I get z to be 8 minus 2w squared over 5. Okay, and then if we wanted to, we could, usually write our input first, w and z. So if w is 0, like 8 over 5. If this is 1, it'd be 8 minus 2, which is 6 over 5. If it's -1, -1 squared is also 6 over 5, and so on. Those are just a few. But we can see when we plug in just these few numbers, I'm not getting any repeaters. And I also can see that I'm not going to get 2 outputs from any input that I put in. And I know you're thinking, well, how am I going to get 2 outputs if for any input? Think about a formula that we've done already this semester that has given us 2 solutions. All right, while I write this answer. So for each, this is how we would answer this word problem. For each W, Z is defined to be 8 minus 2W squared over 5, which is one value. Thus, Z is a function of W. Okay? So is W a function of Z? So I now want W equals. So I want W equal to, we'll learn about something called function notation. So where I put like something like this, but this currently makes no sense. But I want W equals. So I'm going to 2W squared equal to 8 minus 5Z. So I just moved the 5Z over to that side. I then need to divide by 2. So I get 8 minus 5Z over 2. And now W is squared. So I need to take the square root. But if I take the square root, what do I also need to include? A plus or minus. So earlier I was thinking, I asked you guys to think about what type of function would give me 2 solutions. I was talking about, or formula, I was talking about the quadratic formula. That has a plus or minus in it, and that gives me 2 solutions for x, depending on the discriminant, up to 2. So we can see that every time I put in Z, I'm going to get a positive and a negative solution every time. So for each Z, W has 2 values, right? And that's because of the plus or minus. So W is not a function of Z. Okay? And that's how that can show up in an equation. If I were to draw something similar to this, I would plug in 0 and I would get like, oh, when Z is 0, W would equal the square root of 4 and the negative square root of 4. So 2 and negative 2. So not a function of Z. Okay? So if that plus or minus is there, function, it cannot be a function. All right, so we've kind of talked about that common difference, and it was a little confusing depending on which way we wrote it, especially when we were like, oh, the temperature is going down, so I'm going to get a negative common difference. And I was like, oh, we're going to learn something that's more a little concrete. So we're going to call the net change in Y between inputs A and B is the difference between the outputs at A and B. So what that means is it's going to be the output of the latter of B minus the output of A. And we don't have any good notation for output of B and output of A right now, but we will in a little bit. Okay? So let's do an example. So when the wind blows with speed V, which is in kilometers per hour, a windmill generates P number of watts of power, according to the equation P equals 15.6 V cubed. So show that P is a function of V. So I'm already set to P equals 15.6 V cubed. So we can just say that each value of V has a unique P, and that unique means it only has 1. Okay? And that's all. So now we're asked to find the net change in power as the wind speed changes from 7 to 10. So I want to do, so net change here is going to be power at 10 kilometers per hour minus the power at 7 kilometers per hour. We always do the bigger input minus the smaller input, right? So 10 kilometers. So like kind of when we were talking about height, because that net change, the negative versus the positive, is really important to see if we are growing, increasing, a positive net change, versus if the net change is negative, means we're decreasing. So the net change can tell us a lot of information. So it's really important to get it correct versus positive and negative. So the power at 10 kilometers would be when I plug in 10 minus when I plug in 7. So that would be 10 cubed is just 1,000. So that moves that over a few spaces. Minus, if I plug this into my calculator, I get 5350.8. And you could have done this separately to the side. And we would have seen that it is going to be 10.2. And net change actually does have units. I'm just subtracting watts minus watts. So the net change unit is the same as the output. Okay, cool. All right. And now we're asked to express V as a function of P if possible. So let's see if we just can do it. So remember that P is 15.6 V cubed. So I want to show V as a function of P. So I want to get to V equals. So first we need to divide by 15.6. So I get V cubed equals P over 15.6. And V would equal, it's a little v, not a big V, the cube root of P over 15.6. So I took the cube root. Do I need a plus or minus with the cube root or any odd root? No, I don't. So I only have one output. So I'm good. All I need to do is express it as a function of the other one. I didn't have to say if it was a function. So that's it. So now we're asked to find the net change in wind speed if power changes from 1,000 to 10,000. So that would mean the net change in this case would be V when P equals 1,000 minus V when P equals 10,000. That first P should be capital. Okay, so that would be like the cube root of 1,000 divided by 15.6 minus the cube root of 10,000 over 15.6, which would equal, oops, I did it wrong. It should be when power is 10,000 versus 1,000. I messed it up. I need to put the bigger input first. So 10,000 versus 1,000. There we go. So we would get 8.62 after plugging into our calculator and about 4. Alrighty. So then we can see that that's going to be 4.62. And then what is the unit on V? V is our output right now, and I think it was kilometers per hour, right? So 4.62 kilometers per hour. Okay, great. So that's net change, something minus something else. Just got to remember the order. It's really important. And in the next section, we should be able to hone in on how to do that. And we'll get like more tools to better define that thing. But right now, that's how we're going to talk about it. Okay. So this is a really fun little section. We've talked about which charts are functions, which equations are functions, and now we're going to talk about which graphs are functions. All right. So how can I just look at a graph and be like, that is a function? All right. So we use something that is called the vertical line test. There's also a horizontal one. So the vertical line test says that a graph is a graph of a function if and only if, so it goes both ways, if no vertical line intersects the graph more than once. Why is that? A vertical line, let's draw like a little chart. A little graph, I mean, a vertical line goes up and down. Like the horizon would go this way. So that would be a horizontal line. That's how I remember it. So that's a vertical line. That intersects the x-axis. Remember, this is the x and this is the y. So let's say x is 3 here. It's still going to be 3 here and 3 here. So this line would be represented as x equals 3. So if the graph were to intersect this twice, so it's like even just like that circle. Okay, that's a lot. So this circle, that's my function. It's actually not a function. That's my relation. There we go. We can see that it intersects here and here. So that means 2 x values would give me 2 y values, aka 2 outputs, right? So if the graph intersects the vertical line or any vertical line, it shows one input has multiple outputs. Okay? So which are functions? If I can draw a vertical line, it is not a function. So draw this vertical line, that passes, what about right here? Ooh, it's close, but it passes, and same here. And when we see these arrows going up and up like this, I just assume the graph keeps going down and down and down, and it's not going to like change crazy on the end. So I can assume that this passes the vertical line test and say, this is a function. What about for B? Kind of looks like a fish. So I can draw a vertical line right here and it passes twice. So that means when x at this value, it'll give me these 2 different outputs. So no. So not a function. What about the next 2, C and D? So C kind of looks like a smiley face. What are your thoughts? I would say that this is a function. This one, however, well, if I draw a vertical line over here, yeah, it doesn't even intersect it. But if I draw my vertical line here, it crosses twice. So this is not a function. Sad face. Okay. So that's the vertical line test. It's pretty fun. And it's pretty great. All right. So that's all for exam 1 material, right? This is 1.4 that we're just finishing up. So this is the last stuff that will be reviewed on exam 1, which should be on Thursday, I think July 1st. Alrighty, so good luck on that. You guys can now study that once you've done this video. Sorry for the exam completely. All right.